Good morning everyone. I am Dr.N.Nithya Priya, Department of Mathematics, Deakin College Government, Vellore. Today we are going to see Cantor set in this session. I am going to explain the construction of Cantor set and one of its property of the Cantor set. Before that we are going to learn the history of the Cantor set. Cantor set is a set of points lying on a single line segment. It was discovered in 1874 by Henry John Stephen Smith, and later it was constructed by George Cantor in the year 1883. George Cantor himself defined the set in a general abstract way. The most common modern construction of Cantor set is ternary Cantor set. So it is built by removing the middle third open interval, and the process is continued. Then we can construct the remaining elements as a Cantor set. Definition of Cantor set. The Cantor set K is a set of all numbers x in the closed interval 0, 1 which have a ternary expansion without the digit 1. So what is a ternary expansion? The ternary is a term of base 3 arithmetic. A ternary number system can contain only the numbers 0, 1 and 2. So it has many applications. One of the prominent application is computer science and in programming in computer science. So properties of Cantor set. We can see many properties of Cantor set. One is uncountably many elements, and it is of zero measure, and it is compact, no-wide dense set, and it is a perfect set, and it is totally a disconnected set. So now we are going to see the construction of Cantor set. We start with the interval closed interval 0, 1, and we can continue by dividing the line segment into three equal parts, and removing the middle open interval. And we can proceed like this. So I am going to explain this stepwise. First, in the first step, that is in the initial step 0, we can take the interval 0 to 1. That is the line segment from 0 to 1. And we divide this line segment 0 to 1 into 3 sub-equal intervals. That is 0 to 1 by 3, 2 by 3 and 1. And in steps 2, and we remove the middle third open interval, that is 1 by 3, 2 by 3. So let us take this interval 0 to 1, and we divide this interval into 3 equal intervals, 0, and it is 1 by 3 and 2 by 3. And we remove this interval 1 by 3, 2 by 3, and we retain 0, 1 by 3 and 2 by 3, 1. This is how we retain this interval. In this step, we removed one interval and retained 2 line segments. Okay, that is the first step. We removed one interval and we retained 2 intervals. And we proceed with this step. We take 0 to 1 by 3. So in this 0 to 1 by 3, and again we are going to divide this line segment into 3 equal intervals. That is, we multiply this by 3 and 3, so we get 3 by 9. So 0 by 9, 1 by 9, 2 by 9, and this is 3 by 9, which is equal to 1 by 3. And we remove this interval, open interval 1 by 9 and 2 by 9, which is given here. And similarly, we can remove this line segment 2 by 3 to 1. We are going to divide this line segment into 3 equal intervals. That is 3 by 3 gives you 6 by 9, and this is 9 by 9. So the next intervals are 7 by 9, 8 by 9. And we are going to remove this open interval 7 by 9 and 8 by 9, which is mentioned here. So we continue the process like this. Okay. So continuing this process, definitely at each step, we remove the open middle third subinterval of each interval obtained in the previous step. In the first step, we removed one interval, and in the second step, we removed 2 intervals and retained 4 intervals. Okay, the process is continued, and the elements which contains the remaining set of 0, 1 is called as Cantor set. And this is a image of Cantor set constructed. And now we are going to first property of this Cantor set is uncountably many elements. We know that after removing all such open intervals, we have uncountably many elements in the Cantor set. And next we are going to prove that the Cantor set is of measure 0. So Cantor set is of 0 measure. So at each stage, first I explain that the length of the intervals removed and retained are same. Because we removed, we divided the line segment into 3 equal intervals, that is 1 by 3, 2 by 3 and finally 1. So we removed the length as 1 by 3. So the removed and retained intervals are same. And in the number of intervals removed in the first stage itself is 1. So that's why we are taking it as 2 power 0, anything power 0 is 1. So the number of, in the first stage we removed 1 interval, and in the second stage we removed 2 interval, and in the third stage we removed 4 interval, and process is continued, and at the nth stage the number of intervals removed is 2 power n minus 1. And the number of intervals retained in each step. In the first step the number of intervals retained is 2, and in the second step the number of intervals retained is 4, and it continues like that. At the nth stage the number of intervals retained is 2 power n. So let us consider k dash, that is the complement of the Cantor set k as k dash, and we write that complement k dash as closed interval 0, 1 minus the Cantor set k. Okay, k dash is covered, we are going to find the length of the complement of the Cantor set. So the length of the complement of the Cantor set is taken like this, because in the first stage we removed 1/3 of the interval, length of the interval, and in the second stage we removed 2 intervals and the length is 1 by 9, and at the third stage we removed 4 intervals, that is 4 into 1 by 3 cube etc., and at the nth stage 2 power n minus 1 by 3 power n plus etc. See, this is a geometric progression. So this is a geometric progression, and the length is a by 1 minus r. So the first element is a, which is 1 by 3, and we can write this as 1 by 3 into 2 by 3, and this as 1 by 3 into 2 by 3 the whole square plus etc. Therefore this is a geometric progression, and the sum of the length of this is a by 1 minus r, that is 1 by 3 by 1 minus 2 by 3, which gives the solution as 1. So we removed the length of the complement set Cantor as 1, but the original set itself is of length 1. So see, consider 0 to 1, the length of the given interval itself is 1. Therefore the Cantor set k must be covered by means of the intervals whose length add up to 0. So the length of the Cantor set is 0. Therefore Cantor set is of 0 measure. Thank you.